aircraft able to fly further, use less fuel, and still maintain high strength and safety? The answer lies in composite materials. In this presentation, we will explore how composite materials are used in aircraft and aerospace engineering. To better understand their impact, let's move on to a case study that shows how they are applied in modern aircraft. What is the purpose of this presentation? So let's see. First, we aim to introduce composite material and understand how they are used in aircraft and aerospace engineering. Second, we will explain the application, importance, and role of composite material in improving aircraft performance, safety, and fuel efficiency. Lastly, we will discuss the advantages and limitations in composite material as well as recent development and future trends in aerospace technology. Through these three objectives, we hope that we can provide a clear understanding of how composite material contribute in modern aircraft and aerospace engineering. So, let's move on to the next section.
I'm going to talk about the topic of review where composite materials are made by combining reinforcement fibers with a matrix material to create a stronger and lighter structures. In aerospace, common composites include a carbon fiber, glass fiber, and Kevlar. These materials offer a high strength-to-weight ratio, improve fuel efficiency, and excellent resistance to corrosion and fatigue, make them essential in modern aircraft and spacecraft.
I'll be talking about the background and history of composite material in aviation and aerospace. It all started in 1940s during World War II, and according to aviation research by Marsh, glass fiber composite were first used in military aircraft, mainly for wider dooms and fuselage section. And in the 1960s, during the space race, as documented by researchers at Composite World, carbon fiber was developed and NASA began using advanced composite in spacecraft structure. By the 1970s, according to a study by scientific publishers in Material Science and Engineering, commercial aircraft like the Boeing 737 and Airbus A300 started incorporating CFRP in parts such as fairing and doors. And today, in the 2000 and beyond, Boeing and Airbus officially report that composite now make up 50% of the Boeing 787 Dreamliner and 50% of the Airbus A350 covering entire fuselage and wing.
One way they are doing this by using a material called carbon fiber instead of aluminum. Carbon fiber is really strong but also really light, so it makes planes lighter without sacrificing strength. This means planes can fly farther, faster, and use less fuel. Next is Kevlar. Metals are incredibly sturdy because of their unique atomic bonds, where non-metal molecules are typically held together by the attraction between a nucleus and a set number of electrons. Metal nuclei are surrounded by a sea of shared electrons. It takes a ton of energy to overcome the strength and resiliency of their countless bonds. So, when a bullet hits a steel plate, the material can usually absorb all the impact energy before the metal is pierced. Next is ceramic matrix composites, or CMC, are like the superheroes of material because they have so many properties. They are strong, tough, and can handle extreme heat. CMC are also lightweight, which is a big deal for airplanes and cars. Lighter materials mean less fuel consumption and lower emissions. They are also resistant to wear and tear, making them perfect for parts that experience a lot of friction. Metal matrix composite, or MMC, these use lighter metals like aluminum or magnesium as the matrix. Often reinforced with materials like silicon carbide, MMC give very high wear resistance and yield strength.
According to the source provided by Airbus, this section presents the application in aircraft by using the Airbus A350 as an example. Different aircraft components are designed to improve the performance, reduce overall weight, and greater operational efficiency. First is the fuselage, which is the main body of the aircraft. It is made from carbon fiber reinforced polymer, or we call as CFRP. This material reduces the aircraft weight while still maintaining its strength, which helping to improve fuel efficiency. Next are the wings. Composite materials are used because they have a high strength-to-weight ratio. This makes the aircraft lighter and improve the aerodynamic performance. The tail structure also uses composite. They are durable and highly resistant to corrosions and fatigue, which help increase the aircraft lifespan. For the engine nacelle and fan blade, composite material make this component lighter and stronger. This improves engine performance and reduces maintenance requirements. For the interior component, composite materials are also used inside the cabin, such as its panel and seat structure. This helps reduce the overall weight of the aircraft. The floor panels are made from composite because they provide high stiffness and good impact resistance while remaining lightweight. The landing gear doors also use composite materials. They are lighter and offer excellent durability and impact resistance. Finally, the radome, which covers the radar system, is made from composite because it allows radar signal to pass through while protecting the equipment from environmental damage.
How composites are used in aerospace. Large vehicles like the SpaceX Falcon 9, according to SpaceX and aerospace researchers Gardner, CFRP is used in the fuselage and fairing, saving up to 50% weight compared to aluminium, which means rocket can carry more payload into orbit. For re-entry vehicle, according to a study by Frankel and Burnett, carbon-carbon and ceramic matrix composite are layered in a honeycomb structure to form a heat shield and nose cones, with standing temperature 1600 Celsius, something no ordinary metal could handle. And for space telescope, NASA officially documented that the James Webb Space Telescope used 80 gold-coated beryllium mirror, each backed by composite material. Beryllium is actually lightweight yet rigid, allowing it to withstand temperature of 233 Celsius in deep space, making it perfect for detecting infrared signal from the deepest part of the universe.
So, why do engineers prefer composite materials? Well, there are several advantages. First, they are lightweight but still very strong, so the aircraft become lighter and use less fuel. Another advantage is that they resist corrosion and fatigue, which means they can last longer under repeated stress. Because of this, less maintenance is needed and operating costs can also be reduced. That's why composite materials are widely used in modern aircraft.
Now I'm going to talk about limitations and challenges. Despite their advantages, aerospace composite also face several challenges. Their manufacturing process is expensive because it requires specialized materials and equipment. Repairs can also be more complex compared to traditional metal structures. In addition, composite may experience delamination under impact or stress, and recycling them remains difficult due to bonded fiber and resin materials.
First is advanced carbon fiber composites. Recent research focused on improving CFRP by increasing engine strength, fatigue, and impact while reducing overall weight. Modern aircraft such as the Boeing 787 Dreamliner and Airbus A350 use more than 50% composite material in their structures. Thermoplastic composites are one of the most significant research developments. Unlike conventional thermoset composites, they can be reheated, reshaped, welded, and recycled. They also enable faster manufacturing and lower production costs, making them attractive for next generation commercial. So next is self-healing composite materials. They are designed to automatically repair small cracks or damage without external intervention. They contain microcapsules or healing agents that activate when damage occurs. First is 3D printed composite structures are an important recent development in aerospace engineering because they allow manufacturers to create complex and lightweight designs with minimal material waste. It also helps lower manufacturing costs by reducing material usage. Smart composite structures combine lightweight composite material with embedded sensors to monitor structural health in real time. They provide early damage detection, reduce maintenance costs, improve aircraft safety, and are expected to become a key technology in future aerospace engineering. Sustainable composites are environmentally friendly materials that improve aircraft sustainability. They use bio-based resins for renewable resource and recyclable composite material that can be reused. Their lightweight properties reduce fuel consumption, lower carbon dioxide emissions, and minimize the environmental impact. Space exploration applications use advanced composite materials that are radiation resistant to protect spacecraft from cosmic radiation. Their lightweight structures reduce spacecraft mass, lower launch costs, and improve fuel efficiency. They are also suitable for long-duration missions because they can withstand extreme temperatures and harsh space conditions.
In conclusion, composite materials have transformed the aerospace industry by improving the performance and fuel efficiency. Their lightweight strength, durability, and resistance to corrosion make them ideal for modern aircraft and spacecraft. As technology continues to advance, future innovations are expected to expand the use of aerospace composite even further.